proprietary Unixes for many years, and now doing performance work at Red Hat in the Westford Performance Group.
And I've been a kernel engineer for Red Hat for about 7 years, doing a lot of kernel work before that too. So our talk's going to be, Joe's going to talk more about the user space side of things. I'll probably talk a little bit more about the lower level technical stuff.
So what this is about, there have been many talks for years about NUMA, what's it about, and how to set up controls on your, both on the outside when you're launching your application and on the inside when you're coding it, to try to make sure that the placement of your memory and your processes are co-located and to take best advantage of NUMA. And this is more of a talk of NUMA, that's NUMA 101, this is the NUMA 102. How do you know you got it right? And we're going to talk about some things you can do today, as well as some very interesting technology that we're working on in Westford that will be available soon at a rel near you. So, very briefly, the assumptions. This is, much of this has been discussion talks in the past. NUMA control is probably the more popular option of how do I place my memory and my processes so that I can get the best location on NUMA. I'm not going to go through all these in detail. NUMA-D is an interesting one. There's a talk later on this week that will talk about it, but it will automatically move memory and processes around to optimize things underneath the covers. And now we're going to get into how can NUMA hurt your performance, and how do you find out?
So before we start that, we kind of want to sync everybody up in the background here. How many people are familiar with the CPU and their caches, the L1s, L2s? Okay, good. We'll breeze right through this then. So we're all familiar that CPUs all have L1, L2, L3, or LLC caches. And those are the easiest places to get your memory. You want most of your application data to be kind of residing there for the fastest access. If it's not there, then going to the local memory is another cheap and easy place to get your data. And then when you get into the NUMA world, you can get your data across at a remote node inside a remote cache. That starts to get a little bit more expensive. And then one of the more expensive places to get your data is in a remote memory location. Just the way, the latencies to get across to NUMA nodes is pretty high, so your costs go up. And well, we want to try to keep everything in the local NUMA node. And then here's a more extreme case. As NUMA nodes are usually 2, 4 nodes. Sometimes you can get up to 8 nodes. So this is one of the more extreme cases when you have more than 2 nodes. Is that you can have memory on node 0 here, or a CPU on node 0, request memory on node 1. The node 1 memory controller can say, well, it's being owned by memory node 3. So now you got to jump all the way over here to find out what he's doing in the line, if it's modified or whatnot. So it's just another indirect, it's another latency that you want to try to avoid. And we're going to try to talk about some tools today to kind of help detect and prevent
Where this can get expensive is, suppose this CPU down here modified the address location that you're looking to read or to modify yourself. And let's say that it's owned on memory in node 1. This cache line may have updated, let's say the value in memory is foo equals 5, and this modified it to foo equals 6. Before this, you can get a value back to your load to say foo equals 6. It has to be updated in main memory. So there's a lot of underlying handshaking that goes on, which costs you time in this process.
So let's figure out how to apply this. So in the real world, you have your processes all on separate CPUs. They're all accessing memory locally, and they don't overlap, and everything's cached in the L1, L2. This is an ideal scenario. As things get a little bit more complicated, in this case, we have process 4 for some reason it's accessing memory in a remote node. It's a little bit more expensive because you have to go to the remote memory to pull it down, but it's a one-time hit. Cache it locally, and then you just move on. Next. And this is our important slide right here. This is kind of the focus of our talk right here. And this is where you get into cache line contention in the memory here. In this example here, we got two processes, process 0, process 4, two different nodes accessing the same memory right up here. And what happens is, because they're accessing the same memory, and the way well, they're accessing the same memory. In the read cases, it's not too bad. You pay the performance penalty once, you read it, store it in a cache. But as soon as one of these processes modifies the data in memory, all of a sudden you run into a giant cost. And what that is behind the scenes, when, say, process 0 modifies the memory, then later on process 4 tries to access that memory, the way the cache coherency protocol works is that, this memory controller is going to have to flush that data back to memory. It's going to have to invalidate the cache line, and it's going to have to send it, allow process 4 to exclusively reserve that line in order to read it. And it's just a whole bunch of transactions that build up cost and latency, and it's something we're trying to avoid. And this is only two processes. And as you have more threads, or in some cases when you have system-wide shared memory and you got a lot of threads or processes accessing it, things really start to build up and explode and to bottlenecks. And
think of it as a queue. The more processes you have, the more they have to stand in line behind each other and wait to get their turn at the modified memory.
And so anyway, so the focus of our talk is really to kind of show tools that we're going to use to detect this problem. We're going to talk about how to fix it, and we're going to talk about internal tools we're using to kind of verify that you got it right and that this problem has been resolved correctly. So this is an important slide.
So on the last one, that was an example of sharing, true and false sharing on cache lines. And what is true sharing, false sharing, and how much can it hurt? Who's familiar with true sharing and false sharing? Show of hands. Okay. Two NUMA nodes and cache lines. When you go to memory and ask for a piece of data, let's say you want to load a byte from memory, you will get a whole cache line of memory loaded into your cache. And on the x86 line of processors today, the cache line size is 64 bytes. And so when you ask for a byte, 8 bytes, however, you're going to get all 64 loaded into your cache. If CPU 2 is modifying this cache line at offset 0, and CPU 7 is reading it or modifying it, that's true sharing. True sharing is when two threads of execution, processes or threads, are modifying the same memory location.
An example of that would be like a lock, a typical spin lock, mutex, futex, they basically access the same memory offset, and you're just kind of competing back and forth to see when it gets updated.
What happens when processes contend for the same cache line? Means you're exhausting the cache line because it's a four-set associative, and you're exhausting all these four. That's a
Yes, we are not getting into the associativity.
Right.
Let's say you have an 8-way associative cache, then you have 8 addresses that could collide, or I mean, once you go beyond 8 addresses that can map differently, now you start to collide. That's not something that happens less often, but it's not something you can control that easily. So that's not part of our talk.
You can only know you have it.
Right.
Yes. So true sharing is when two threads or processes are modifying the same memory location. False sharing is when, take that same scenario, but you're now modifying different locations in the cache line. Today's processors are pretty quick at resolving true and false sharing when it occurs on the same NUMA node. When it occurs on different NUMA nodes, that's when your performance can really pay a price. So here's an example that we ran on a 4 CPU box. And this is an extreme example of how much true and false sharing can hurt. On node 0, I took 2 processes that continuously modified their own location in memory. On one CPU, we modified offset 0. On another CPU, offset 8. And to start out, we had 3 other nodes in there just continuously reading from this cache line. And we computed how long it would take for these 2 threads to go through a loop 200 million times. And then we switched the reads. Instead of reading from this cache line, we decided to have these 3 processes on these NUMA nodes read from this other cache line while these 2 were moving along. And what we found was this green bar. It took half a second for those 2 threads to go through 200 million read-write cycles when they were the only ones modifying their cache line. When I took just one of these readers and moved one of them up into this cache line, it slowed down these 2 reader-writers to 4.5 seconds. It now took them 4.5 seconds to do what they used to be able to do in 1 second. When I moved all 3 reader-writers over to read from that cache line, it slowed down those 2 threads to over 10 seconds because they could no longer, they now had to contend with giving up ownership so the other threads could read the cache lines. That's an extreme example, but it shows the penalty. So now, some tools, how to diagnose it, some techniques and tools available today, and some of the things that will be coming soon. We're going to talk about 4 tools here. NUMA-stat. How many of you have used NUMA-stat? The one available in Rel 6.4 actually is a lot more enhanced than previous versions. It shows individual PIDs and their individual memory usage, what type of memory and where it's located, where before it was more of an aggregate. So if you can get the one in Rel 6.4, it's a lot more powerful. Excuse me?
It will work with Rel 6.3.
I believe it does. Copy it back to Rel 6.3? The person who enhanced it is sitting in the corner of the room, Bill Gray.
I believe it will work on Rel 6.3.
I think I've done that.
There's lots of other things to make one on Rel 6.4 too.
Perf, the Perf tool that's been available. Now we're going to talk about 2 new tools. There's one upstream that's available in the 3.10 kernel, and it's an enhancement to Perf called the Mem Loads Event. And then there's a cache-to-cache sharing tool that will be folded into Perf in an upcoming release. This is what we're working on in the Westford Red Hat office. We did all our work on a Intel Sandy Bridge processor, Ivory Bridge processor. So I took spec JBB 2005 and I ran it in a mode where there was one controller, small controller, and two backends, two instances that did all the work. And here's a NUMA-stat on Java, and it shows that the first PID is very small, and I didn't bother placing it. The second PID I placed the memory on node 0, and the next PID I placed the memory on node 1. And NUMA-stat showed us, when I executed the spec JBB program, that was my intent, and sure enough, NUMA-stat says that's where your memory is. Well, that's great. The memory looks reasonable, but how do you find out if your CPUs are co-located where your memory lives? And there are several ways. One way to find out is in the /proc/PID/status file, you look up your PID, and there's an entry called CPUs allowed list, and it says here are the CPUs that this PID is allowed to run on. And sure enough, these are the 2 PIDs that I'm worried about with all the worker bees for that Java. And sure enough, they can run on these processors. And then the question that is often confusing on every change of hardware is, well, what NUMA nodes do these CPUs belong on? And if you look at the top few lines here, NUMA control -- hardware, if you grep for the CPUs, it'll tell you what CPUs belong on each individual NUMA node. So at a high level, we now know we ask for a given Java PID to be placed on a given NUMA node, and we can verify that the CPUs that's where the CPUs are executing, and that's where all the memory lives. That's well and good. What we don't know is are any of those processes that are running on each NUMA node accessing each other's memory? And if so, are they contending with the same memory, the same cache lines? If that's happening, what CPUs are they running on? Which ones are these CPUs? What are their PIDs and their thread IDs? What are the data addresses they're accessing? Where in the application? So tell me the PC, the instruction pointer, so I know where in the code to go look. And are they reading the cache line or are they modifying it, and how often? These are the key questions to get answered for true and false sharing across the NUMA nodes. So we have another example here. And by the way, this tool that we're working on just came into being in the last month or so, and we only have it running on one box. So as we slowly start to work it out, we have a lot of patches on it. We ran LIMPAC, and we have the machine we have is 2 NUMA nodes, 20 CPUs, logical CPUs on each node, and so 40 altogether. We ran LIMPAC with 40 threads, and we got a certain performance point, and it was all well and good. Then we bumped the thread count to 60 threads. So now we had about 1.5 threads for each CPU. And lo and behold, when we ran it with 60 threads, it slowed down about 3%. And the question is, can we learn anything? Taking the Perf Tool, as Will Cohen spoke about in his earlier talk.
Are you guys familiar with the Perf Tool? A lot of you guys, some of you guys?
Just running Perf on it, Perf defaults to cycles, and we can, all of a sudden, when we're running with 60 threads, we look and see that the kernel scheduler is now the hottest function in the entire LIMPAC program. So what's happening here? It's taking 16% of the time. And what I don't show here is when we ran it with 40 threads, the kernel scheduler was only taking 0.3% of the total runtime, CPU cycles of the program. So why did it jump from 0.3% up to the hottest routine, 16%? When we also look at the Perf report, we see that the majority of its time is spent on a lock bit test and set instruction. And so the question is, why is it so hot? So we run a number of perf counters, and we also see that it is getting the hottest, it is the hottest routine for last level cache store misses. When it's trying to write to a given memory address, it misses out of the last level cache. And it's the hottest routine that does that. Excuse me?
How do you see it from this point?
Last level, we asked Perf to say, show us the last level store misses, last level cache store misses, and this is the output it gave us. And when we said, all right, show us the annotation of the code for the hotness, again, it was on this same instruction. So the question is, why is it so hot? So what we know we're executing most of our cycles are on that one instruction, and most of our last level cache store misses are on that one instruction. And the question is why? Is it because we're waiting for data from local memory? And if we add prefetches, will that help? In this case, prefetches will only slow it down even more. Are we waiting for memory from a remote NUMA node? Again, this prefetches will slow us down more. Are we waiting for memory from a remote NUMA cache line? And if so, why are we waiting for it? Someone must be modifying it. Who's modifying it? So here's some of the early output of that cache-to-cache sharing tool that will be folded into Perf. And this helped really explain what was going on. Cache line 0, we see the Linux kernel scheduler modifying a data address, and it's doing lots of reads, that's reference counts, and lots of stores. It's one instruction in the scheduler, and when we looked at that one instruction, it was the locked bit test and set instruction. And what we realized was, and by the way, this also showed us, it's the kernel scheduler, it's running from the kernel, And here are all the CPUs that executed on. And we can see that the kernel scheduler is running on every CPU in the entire box. So across node 0 and node 1. And so here's a scheduler modifying the same data address. When we went into the code and we looked, the kernel has a CPU list, which is a bit mask for every CPU it has. And this is a 40 CPU box, so there are 40 bits in this mask that this one scheduler routine was modifying. And the memory, it lives in one place. So if you're on node 1 and you're modifying it, you're tugging the cache line over to node 1. Then the CPU on node 0 says, well, I got to modify it because I'm now updating it for another thread, and it tugs the cache line back and forth. So the tugging of the cache line back and forth was the primary reason why the application slowed down and why the scheduler all of a sudden became the hottest routine in the whole program. Any questions on that? Okay. So remember, we previously showed this example that I spoke about a few minutes earlier. That was run on a four node server. Again, we instrumented it on a 2-node server to see if this tool could tell us what's happening. We have 2 nodes. Node 0 is doing all the reading and writing of these 2 cache lines, and node 1 is just reading these offsets in that same cache line. Again, the cache-to-cache sharing tool shows us we have read-write thread number 1 and read-write thread number 2. They are doing lots of stores, reads and stores to that data address that ends in 80 and address that ends in 88. Here's the process ID and the thread ID, 2 different threads. Here's the program and the program name and the CPU number as well as a node. And then the 3 reader threads. They're running on a different node, different CPUs, and they are primarily doing all reads. And this really shows the tugging back and forth. We now know the hottest cache line, the data address being contended, the names, the process names, the address of the instruction address, the PID, the thread ID that's causing the contention. All the information we need to solve it. The rest of the cache lines got much colder right away.
All right, I'm going to talk about an example using another tool, another Perf event called Mem Loads that's only recently been added to the upstream kernel in the 3.10 kernel here. To start, I want to set up the example. I started with a test. I had 2 processes running on 2 different CPUs. And it wasn't doing much. All it was is I used 2 locks, and all they do is each process was acquiring a different lock and then releasing each other's lock. And the idea was to do a ping pong, a controlled ping pong back and forth. I could use 1 lock, but then you kind of get unfairness involved. Like one process would spin maybe 100 times before the other process got a chance to grab that spin lock because of the way the latency on the NUMA side thing. So I used two locks to easily go back and forth in a nice controlled manner. You can see the locks are on different cache lines. So you start out by acquiring the 1 lock. The process A just does some nothing loop, releases lock X or lock Y. Process B acquires lock Y, does a bunch of nothings, and then releases lock X and just keeps ping-ponging back and forth. Now this particular test was trying to measure something called we call it a hit M. And what that means is you're trying to do something called a cache hit on a modified cache line. And previous on, when I talked about before that important slide, what it was is when you had one process modifying data, and another process was trying to read that modified data. Well, that's called a hit M. You're basically reading a modified cache. You're doing a cache hit and someone modified it. We're trying to catch that scenario, and the reason why we're catching that scenario is based on experience is that that's one of the more expensive operations to have, especially in a NUMA scenario. So we thought, okay, let's focus on that and develop some tools and techniques to find that, figure out how expensive it is, and then we can go about fixing it and verifying that we fixed it. So next slide. So again, like I talked about, we got two processes ping-ponging back and forth, generating hit M's. I ran this test twice. I ran it once across NUMA nodes and then second time on the same NUMA node. And there was about a 15% speed up just by migrating this from a remote CPU to a local CPU. So let's dive into some techniques we use to figure this out here. So using Perf, Perf record uses the default cycles event. It just shows that the spin routine was the hottest routine there. This is an expected thing. You know, it's basically just acquiring the lock all the time. You annotate the file, and you see it's basically in the acquire lock. It's just sitting there loading the lock all the time and just reading it, just trying to wait for it to be updated so it can move on. This is all expected stuff. So our idea is like, can we learn why this is so hot? So go to the next slide. So I use another event that Perf has. It's called a Llc Load Miss. It's basically how many last level cache misses did I have? And this is important because this means you missed a last level cache, you probably went across to a remote NUMA node. So here we do again, we see the spin routine's the hottest one. It's,
it's a remote NUMA node and not just memory because you...
That's true. That's a good point. You're right. This basically tells me that it went off the chip. It could be local memory, it could be remote memory, it could be a remote cache. Very good point. Thank you. So now we see that this spin routine's going off the chip for some reason. It's missing the last level cache. We don't know why. Again, it's doing the locking stuff. So the question is, where is it going? Why is it missing the last level cache? How can we learn something? How can we figure this out? So, next slide. So this is where we come with this Mem Load event. And what this Mem Load event does in Perf, it gives us a lot more detail out of the hardware. The Ivy bridge we use captures more data besides just an IP. It gives us the data address you're having, the source of where that load came from. In this particular case, we could see we're looking for hit M's. That was the important part we were looking for. And we could see that the access came from a remote cache one-hop hit. So this implies that it wasn't local memory, it wasn't remote memory, it was actually a remote cache. It was only one hop away. So like, okay, so this sounds like a classic NUMA problem. Okay, you got data stored in another remote node.
And it's modified.
And it's modified.
What would it charge if it's just poor locality? I would see it from a local, it's just to call from...
I'm sorry, can you repeat the question?
It's a poor locality.
It's a what?
Poor load.
Or poor...
Poor locality of the process means it has a huge data set which it reads randomly everywhere. Then what would I see then?
Because it's modified, meaning it's saying here that you had to go to...
No, I know, but what would you see?
Oh, what will you see if you're getting it from a remote memory? Or
Yeah.
so if it's clean, but it's in another NUMA node's memory.
It would probably, the snoop would probably be none, and this might be just remote memory. There's a lot of options. I haven't seen all the options. We've been focusing on hit M's, but
That is a good question.
this access should say, I think, I'll probably say remote memory. I don't think there's a need to, there's no snooping going on, so this should say none. But there's a lot of options. You can hit modified, hit forward, hit shared. Access is L1, L2, LLC, remote. I haven't played with a lot of the options. I'm assuming there's a remote memory option there that would answer your question. So now we're trying to, so now we can see here that most of the contention is from the remote cache. And the next question we want to ask ourselves, how can we minimize these remote accesses? Because as we talked about before, this is an expensive operation. So the usual fix for this is you want to migrate it from a remote node back to the local node. Some people use NUMA control. This particular program I use set schedule affinity. I just bound the two processes on the same NUMA node. And I basically reran the same tests again. So here I am running the perf cycles event. Same thing as we saw before, the spin routine's the hottest routine, doing all the locking, annotation's the same. This is all expected. We're like, okay, let's continue our investigation and see if anything else has changed, or if we verify or continue our verification that we've actually resolved the problem. Next slide. Here I'm looking at the Llc Load Miss event, and now I notice that my spin routine's gone. And this is usually a pretty good indication saying that, okay, now everything's being hit in you can assume that everything's being hit in the LLC cache. because you're not going off chip anymore. So this is a positive step. We also noticed that the Llc Load Miss event dropped from 40 million down to 779K, which indicates that we're doing a lot less off-chip accesses. But we're not really positive that we're still doing the right thing. Looks like everything's doing LLC hits, but we're kind of guessing. We don't have any proof yet. So let's go to the Perf Mem Load Event. And here's our proof. This is the proof we were looking for, our verification technique. And we look here, we look for the hit M's, as we were doing before. Now we see these are all L3 hits. And this is what we expected, and this kind of verifies that by migrating it to a local node, everything's working as we expected. And our performance in this particular test case went up 15%. So this is good. And now we've kind of verified everything. And as we talked about before, the latency from the L3 cache is a lot lower than latency from a remote cache. And so this kind of through the verification step that we're kind of missing today, where a lot of times you kind of guess by putting, you migrate process over to local node, and you kind of guess that everything's working correctly, but you don't have a verification to say, well, is it, all the performance gain really coming from the migration, or is there some other hidden performance problems? And this shows us that everything's just L3 hits, so everything looks good. Next one. And this is just a summary slide. Ways to mitigate your cache contention. Talk about that.
It may seem counterintuitive, but if you have variables that are frequently modified, putting them in their own cache line, even if it wastes memory, really helps performance. We did this on I did this on several companies in the kernels that I worked on in the past, and putting modified like locks in their own cache line made us a big difference, especially with scalability. So adding padding, it may seem like you're wasting memory, but there's a big trade-off that you gain in the end. Aligning your data buffers on structure boundaries. If you don't know where the alignment is, and GCC and every compiler out there has directives to align the memory. If it's dynamic memory, you can use, if you're allocating dynamic memory, you can always just mask off the addresses so that your data structures start on cache line aligned boundaries. Lowering the granularity of locks. I mean, there are examples where we're working with a developer who just ran into a locking problem, and they were taking out a big lock for a whole bunch of semaphores, and they modified it so that just each semaphore would have its own lock, and that helped things, but really what it helped was, instead of having a whole lot of CPUs from across the system contend for one major lock, they're now all going for their individual locks on different cache lines, and they can go get their individual locks separately. They're not fighting for the same cache line. And as we talked about, trying to get each process together on the same NUMA node, each process in memory, co-locating them on the same NUMA node. Something let me go back to. In a previous company I worked for, we had new hardware that I think went up to 128 CPUs and 8 NUMA nodes. And we're working with a database vendor for a good TPC number and for a benchmark. And we couldn't get it to scale. And for about 2 months, we were working with a database company, kernel engineers, and I was in the compiler group. And we hit a bottleneck, and we saw that these memory accesses were stalling, but nothing we could do. No one could figure out why. And someone in the company developed a similar cache line sharing tool. And what we found was, in a cache line, there was one process that was keeping track of the sequence of transactions that occurred. So they were modifying, just incrementing a sequence count, saying, I completed a transaction. And elsewhere in the cache line, all the threads, there were hot red variables elsewhere in the cache line that all the threads across the whole box were reading. And that killed the performance. And as soon as this tool, that cache line sharing tool could see what was happening, and basically the information I showed you earlier about who's tugging on that cache line. As soon as that was seen, a 5-minute fix to take that hot sequence counter, put it in its own cache line, and 18% speed up in the TPCC benchmark. 18% in TPCC just from that one move. I mean, that's a classic textbook example of you don't find those types of wins every day, but it was pretty cool.
But as you point out, I mean, this is all comes down to having the right tools to kind of expose the data you need, and the hardware. You know, especially we did all our work on XA6, but you know that hardware has a lot of the PMU, the performance monitoring unit, has a lot of data that it exposes, and kernel and the user space is starting to slowly get access to it and exposing a lot of this data, so you can make better decisions. You can get better visibility into your application to see, you know, cache contention issues like this easier.
Shared memory. If you have large NUMA systems with shared memory, lots of threads running on different nodes, you're ripe for cache line contention. And
what happens with, say, Oracle, where you have large shared memories and a huge number of processes on the same system? Did you have an opportunity to look at it?
we will be getting Oracle on this box. Yes, we run Oracle in the Westford office for performance benchmarks, but as we said, we just got this running on a 2-node box, and we want to get the kernels, we want to upgrade our other bigger systems and get some kernel patches on there so we can run it. So
yeah, but we're hoping to use these tools on, you know, various databases and other big applications to kind of, you know, expose these type of problems and fix them, so we can really tune them for RHEL, and you know.
And then we'll fold it in upstream into Perf and get it upstream. So just to recap the tools we were talking about, NUMA-stat and Perf are available today. Perf with the Mem Loads option, Mem Loads Event, is available in Fedora. The current Fedora or the next?
Well, not really in Fedora yet.
Okay.
It'll be whatever 3.10 kernel, maybe in a couple months you might see it in Fedora 19, but not right now.
And it'll be in RHEL. And this cache-to-cache data sharing tool that we mentioned will be folded into Perf as well.
Will those be in backported to RHEL 6 or be in RHEL 7?
It's a good question.
We can't commit for RHEL 7, but they will not be backported to RHEL 6.
Okay.
Because of,
but they might show up in RHEL 7.
We're hoping that we can get it into RHEL 7. It's a matter of how and when.
I mean, we're not in any position to commit to schedules, but
yeah.
That's. So the key takeaways. You can look at a high level with NUMA-stat and say, okay, all my threads and processes, threads in memory are executing over here and located here, and others are located here. All it takes is one process to reach across and grab a cache line on another node and be modifying each, you know, tugging at someone's cache line to pull your performance down. So either you could be accessing someone's cache line or some remote user coming in and accessing the cache line on your local node, and you could really hurt performance. As we just mentioned, if you have lots of shared memory, locks, or common threaded data, you're prone to this behavior, and better tools are on their way. That's it. Any questions?
Is your C2C tool, is that something that would be in an R&D environment, or is that something, are you targeting it for production use?
We will be rolling it into Perf, the Perf tool that is available. So it'll be a Perf dash. Right now, today, you have different events, and it'll be an option to Perf.
Do you have a rough idea of the overhead to do that type of?
Similar.
It's no different than the current sampling overhead. I mean, it's just basically, you ever use Perf Record? Or have you used a Perf tool at all?
Some, not
Yeah, so it's the same. It basically, the CDC tool is just basically using the same type of interface that Perf Record uses, a Perf stat. Actually, I'm not Perf stat, Perf Record, where it does a sampling at a certain specific rate. It grabs just a whole bunch of data records, and we just process it differently. I mean, Perf Record outputs it in a nice pretty little tree that you can see the call trace. We take all that data, we grab latency information, memory access information, and just present it in a different data. So it's the same overhead as perf record, but we do it in a system-wide mode, which is a little bit different. So there's an overhead. We haven't quite measured what the overhead is, but there will be a little small performance hit. But the idea is we want to be able to run that. The idea behind the tool is that you got your application up and running, doing the background. You run this tool, and it's going to go profile in system-wide mode. So you kind of sample everything, all the memory accesses and everything, and you run it for, I don't know, a few minutes or something, or whatever data spikes you're looking for, and then you exit out of it, and then you post-process it and see what happens, and see if you can glean any information out of there. But you know, it's unfortunately it's not something you can keep running all the time. I mean, it'd be nice if their overhead was low enough that you can run it in the background, not have to worry about it, and then just anytime someone complains about performance problems, just grab the data, snapshot the data, and see what's there. But unfortunately, we can't.
The other question I have is on an active system with lots of threads, 10,000 or so threads. How deep in the weeds is the output data from a 1 minute recording? I mean, are you going to be able to discern, process A, thread A, is contention with
The hottest cache lines rise to the top. They're sorted by the hottest cache line.
Yeah.
So,
I mean, it doesn't have to be 1 minute. It could be an arbitrary number of minutes, and
I
each.
was just trying to see if you're going to be overwhelmed with data. This is where I was.
Well, we don't care too much. I mean, everything's got its own thread ID, and we're just looking for whatever hottest cache line contentions are. Basically, we read through all the records, and we correlate it all together. Say, okay, we're basically sorting on the data cache line. So what data cache line is being accessed the most? That's going to propagate to the top, and then you're going to see, okay, what PIDs or threads are accessing it, and then we look from there.
If it is causing too much interference, you can reduce perf's sampling rate.
True.
And so you can run it longer with a lower overhead and accumulate the same data. So,
It's almost a quantum mechanics problem.
and in reality, the way this is done is we're sampling for off-chip event, off-NUMA node events. Like when we look at threads and say, all right, I did a load, and I got my response from a modified cache line on another node, and you go get the information, you find out where the other node is. And around the same time, you also say, I stored to that address in that NUMA node, and you get thousands of these events, and you coalesce them together, and you look and say, well, gee, this thread has been modifying this cache line a lot, and this thread's been reading it and missing on it, and you align the addresses, and you do a lot of post-processing.
It'd be interesting to see if you had an increased number of NUMA nodes on the same size box to see if that would modify that push-pull.
You say increase the number of nodes?
Yeah. So you had a larger number of nodes with smaller numbers of CPU per node.
So go from 2 nodes to 4 nodes, but
Yeah.
decrease the number of CPUs?
Yeah. I wonder if that would modify your data set.
Would you expect that to give you better performance?
It might be better performance because latency, your locality might be different.
I guess it depends on the application. If the application is small chunks of threads, then yeah, you're right. Maybe you can spread it out.
The latency between the two, because the locality would be close enough where it would be less.
Yeah, but
Right.
if you have to access a remote node, then it might be much more costly if you have more nodes.
I mean, that would be the interesting thing to see is if I had more nodes, the cost of the more nodes might be greater than the savings of the locality.
Well, I think what you're trying to point out is if you have 2 applications that are doing a lot of read modification of the same cache line, they're going to thrash the caches. So if you split them across different nodes, then they're not going to thrash the cache as much. But that only works if you have a small number of threads. If you have 10,000 threads, then
And that's that.
it doesn't matter.
You want a larger number, or smaller number of nodes that are.
You're right. You're going to want large number of CPUs and minimize the number of nodes. Right.
Just to mention, we don't have it here. There's a tool that Intel put out that can be downloaded. It's called NUMA-Top, and it will, I believe it needs a 310 kernel,
Yeah.
and it will help show you the percentage of remote NUMA accesses your application is making, memory accesses, and it'll sort them by the hottest. And let's say your program is an A.out, and let's say that's the hottest. It'll show you 30% of your memory accesses are local and 70% are to remote NUMA node. And so it's a good first level view.
So something like your 10,000 node thing or 10,000 thread thing that might give a gross level view of what's happening.
Right.
Yes, where hopefully then this one will tell you exactly where and why, and you can figure out.
So you said you had done the testing on the Oracle?
We have not tested with Oracle.
Because it's interesting to see in Oracle rack environment, it does provide some clustering and in RDMA kind of environment. Does it complement or do you see any bottlenecks with that?
It would be interesting to see.
It'll be interesting to see.
Yeah, we're looking forward. I mean, because yeah, they do a whole bunch of tweaks just to kind of segregate the memory and see how well it works.
Does NUMA-D do anything to self-cure any of this, or is that?
Sure.
NUMA-D, Bill's the developer of NUMA-D. He doesn't have a microphone. It will align processes and memory together on the same nodes. Now, when you have something like Oracle where you're all dealing with shared memory, you can't move the entire shared memory to one node or another. You have to sort of interleave it, and so it tries to respect. It tries to learn what it can do with that. So, Bill, will you be saying more about NUMA-D later in the week?
The performance talks on Thursday afternoon.
Thursday afternoon?
Between 1:20 and 3:30, I think.
Okay.
Will be discussed there. Or stop by there's a performance booth. 9:26.
He'll be there. Well, many of us will be there at the performance booth to talk about NUMA-D.
Do you plan to put out a white paper or a study on this that kind of lists your testing methodologies and the results at some point?
We should. Our
can.
group
That would
puts
be
out
great, 'cause
performance
that would be very
briefs.
useful for especially not only you guys, but customers of mine, so that we can
Yep.
look at this.
Okay. We were hoping this could be, that we had at least a month's worth of more data that was available a month earlier, and then we could have richer data here, but
Well,
it's,
that and then have the different variations in the configuration.
Right.
yes.
We're still trying to build out the tool a little bit, and once we get that, we want to push the customers as a way of an easy way to kind of investigate data.
We're out of time, but if you have more questions, we'll have a performance booth downstairs. So thank you very much.
Thank you.